Voices of the Satellites, recordings of the radio signals from man's first 5 space travelers. This is Professor Benham in the laboratories at Haverford College, bringing you the sound of man's first satellite. On October 4th, 1957, Russian scientists from somewhere in Russia fired the rocket that put the first artificial satellite into an orbit going around the world once in about 96 minutes. Man's first artificial satellite is called Sputnik, Russian for traveler. After Sputnik had made several trips around the world, scientists were able to establish its orbit. It turns out that the orbit carries the satellite to a maximum distance of approximately 600 miles from the Earth's surface and a minimum distance of 150 miles. The orbit is inclined to the equatorial plane of the Earth at an angle of about 65 degrees. The speed at which Sputnik has to travel in order to stay in an orbit like that is about 18,000 miles an hour, 5 miles a second. It can only be seen through a medium-powered telescope and only when it is in just the right position relative to the Sun. While the 22-inch diameter satellite itself is not visible with the naked eye, the third-stage rocket, which put it up there and which is also going around the Earth, is visible with the naked eye when it is in just the right position. However, the satellite has a radio transmitter in it, which means that the signals from the transmitter can be picked up any time that the satellite comes within 1,500 miles of the receiver. This happens 6 times a day, 3 times in the morning and 3 times at night. The transmitter is sending on a frequency of 20.005 megacycles. Let us tune in Sputnik again on our communication type receiver that we have here in the laboratory and listen to Sputnik as it was going approximately overhead about 400 miles up at 7:39 p.m. Eastern Standard Time, October 21st, 1957. Note that the signal is steady now instead of beeping. This is because the beeping mechanism failed after several days of operation. Valuable information can be obtained from this transmitted signal from the satellite to give us information about the position and distance of the satellite from the receiver. This is done by a very careful study of the frequency through a phenomenon known as the Doppler effect, which is the change in frequency as the satellite goes by. Suppose we illustrate this with an effect with which everyone is familiar. If you are standing by a highway and a car is approaching blowing its horn, as the car goes by, there is a sudden drop in pitch. Listen. When the car passed the microphone, it was about 5 feet away and traveling at 60 miles an hour, which makes the pitch change very suddenly. On the other hand, the satellite is about 400 miles away when it goes overhead and traveling at 18,000 miles an hour, which makes the pitch take about 1.5 minutes to change. Remember that the further away a moving object is, the slower it seems to be traveling. Let us tune in on the satellite as it approaches from the southwest. It will travel overhead at about 400 miles altitude. Remember that the satellite travels about 450 miles during this 1.5 minutes. Now the pitch is beginning to change. Now the pitch is changing most rapidly, which means that the satellite is about overhead. You will notice now that the pitch is quite low, which means that the satellite is beginning to go away from us. You will notice that the pitch flutters a little bit in volume. This is due to variations in the ionosphere. Now the pitch is no longer changing, which means that the satellite has passed overhead and is going away from us to the northeast. In order to make this change in pitch more dramatic, let us listen to 3 seconds of the recording during the time that the satellite was approaching from the southwest, followed immediately by 3 seconds taken from that part of the recording when the satellite was going away to the northeast. From the complete change of pitch which was just demonstrated, the speed of the satellite can be calculated. And the distance to the satellite, when it is closest to the receiving station, can be determined from the change in pitch per second when it is changing most rapidly. Suppose we measure the speed of the satellite. Here in the laboratory we have an audio oscillator whose pitch can be changed by turning the knob. Now, by comparing the pitch of the signal from the satellite with this oscillator, we can determine the change. Now, here is the pitch of the satellite signal as it approaches. Now let us compare this with the oscillator. Now they agree, and the oscillator dial can be read to see what the frequency is. Next, we will find the pitch of the satellite signal as the satellite is going away. Here comes the oscillator for comparison. And now by reading the oscillator pitch, we can determine that frequency. Now, from a knowledge of this change of pitch, with a little trigonometry, the actual speed of the satellite can be calculated at 18,000 miles per hour. To find the shortest distance between the satellite and the receiver is a bit more complicated because we have to determine the rate of change of pitch of the signal and find the point at which it is changing most rapidly, then substitute this into a rather complicated formula. For example, the following recording is the 10-second period during which the pitch was changing most rapidly. Man's first artificial moon is a ball 22 inches in diameter, containing radio transmitters, antennas, and batteries for about 3 weeks' operation. The entire weight is about 184 pounds. As we have already pointed out, the rocket that put the Sputnik into the orbit had a third stage which went into orbit also, so that the two pieces were going around together in the beginning. But every time that the satellite and its casing came down to the low part of its orbit where atmospheric friction could be effective, they would be slowed down. However, the rocket casing, being much larger and much more area than the spherical ball, would experience a good deal more friction. Consequently, the rocket casing would not be expected to stay up as long as the satellite itself. Indeed, this turned out to be the case. The rocket casing disintegrated and came down in the early part of December 1957, while the satellite itself continued for another month and finally came to extinction in the early part of January. Before this happened, however, the world was introduced to the next chapter in the saga of man's probe into outer space. On November 3rd, 1957, Russian scientists launched the rocket that carried Sputnik II into an orbit. The signal that you are now listening to was sent down by a radio transmitter in Sputnik II that was very similar to that in Sputnik I. From this signal, we can deduce the distance and the speed just as we could in the other case.
However, there is a vast difference between this satellite and the first one. Well, for one thing, the weight was 1,100 pounds instead of 184 pounds. This in itself staggered the imagination of scientists, who thought even the 184 pounds of Sputnik I was large. Then, too, the orbit was quite different. The maximum distance was 1,100 miles, and the minimum distance about 200 miles. The satellite traveled in pretty much the same direction as the first one did, which indicated that it was launched from approximately the same place. But these statistics, surprising as they are, were not what made Sputnik II so surprising. We were all amazed to learn that Sputnik II carried the first living thing into outer space. As a passenger, in a special chamber built into the satellite frame, was Laika, a curly-haired dog who had been especially trained for this flight. Especially trained in the sense that he had lived in a similar chamber on the surface of the Earth, under conditions exactly like those that he would experience in the satellite, except for one thing, and that is the lack of gravity. There is no way to do away with gravity on the surface of the Earth, but in the satellite that is spinning in an orbit where gravitational pull is equalized by centrifugal force, Laika, as well as all other parts of the satellite, would be weightless. Imagine living under conditions in which if you turned over a glass of water, it wouldn't run out. Or if you lifted your hand to scratch your ear, you would be likely to box it severely. Now, of course, the Russian scientists wanted to find out as much as they could about what happened to Laika up there in the satellite. They had the chamber equipped with the necessary food and oxygen to keep Laika alive, but they wanted to find out what happened to the circulation, for example. So they attached a small special microphone near Laika's heart and connected the microphone to an amplifier, which then was connected to one of the transmitters that was located in the satellite. On November 6th, after Laika had been up there for 3 days, all seemed to be going well, and her heartbeat sounded like this. And the next day, it sounded like this. Perfectly peaceful and seeming at rest. One night when we were looking for the signals from Sputnik II, an amusing thing happened. There, right on the frequency of the satellite, was a weak, plaintive signal sending from somewhere far away in Morse code. And when we translated it, we found that it was saying, bow wow. It turned out later that someone in the South Pacific was exercising his sense of humor. Although the Russians were first to put a living creature into an orbit around the Earth, there is strong evidence to indicate that the equipment they used was developed at the Naval Development Center in Johnsville, Pennsylvania. Thus far, we have talked about and listened to 2 of man's first 5 satellites, Sputnik I and Sputnik II. What the Americans were doing about this, meantime, will be told on the other side of Voices of the Satellites.
The first one is the beeping Sputnik I. The next one is a recording of the Doppler effect for Sputnik number 1, recorded at 7:39 p.m. Eastern Daylight Saving Time, October 21st, 1958. The following is a recording of the Russian Sputnik number 3, launched 2:41 a.m. Eastern Standard Time from somewhere in Russia on May 14th, 1958. The following recording was made under rather interesting conditions. I predicted that at noon on that day, the satellite would make its first passage over the Philadelphia area, but I couldn't be here at that time, so I set the receiver and the recorder and a timer and went away and left it. And when I came back, I listened, and here is what I had.
Next is the heartbeat of Laika, the dog, in Sputnik II, recorded on November 6, 1957. Fading was quite severe that night on account of aurora borealis display, so we have taken 10 good clear heartbeats, repeated it several times, and spliced them together. The splicing is not perfect so that the break in rhythm is obvious.
Let us continue the story of the satellites by introducing the American space travelers. On January 31st, 1958, at 10:48 p.m. from Cape Canaveral, Florida, the Army launched with Jupiter C rocket America's first satellite, known as Explorer 1. This was a satellite weighing about 30 pounds and containing numerous electronic instruments to send back information about cosmic rays, temperature, meteorites, and the like. This recording is going to bring you the sounds of some of the signals from Explorer 1, as well as those from the Navy's Vanguard and Explorer 2 and 3, as we received them here at Haverford College. The signal you are now hearing is Explorer 1 as it passed over the first time after its launching. Note that the pitch is decreasing, indicating that the rocket is approaching us. Now it is at about as close as it is going to get, and you can hear the modulation of the telemetering equipment in the background. And now the pitch is rising, and the satellite is beginning to go away from us again. It is traveling at about 18,000 miles an hour, and it is about 250 to 300 miles above the Earth, passing at the 34th parallel at about 75 degrees west longitude. Now, of course, these satellites were put up there for a reason, other than just to put up a satellite. There's information that is desired about cosmic rays in outer space and temperature, and how many meteorites there are per second, and things of that nature. Inside of the satellite are instruments to send back that information. This is called telemetering. Here on Earth, we have radio receivers that can pick up this information, translate it, and give us some of the answers. This is what that sounds like from Explorer 1. You will notice that there seem to be two tones, and that the length of duration of the sound of each tone varies. This is the way the information is transmitted. Now, there were two transmitters in Explorer 1. The one you have heard so far was 60 milliwatts power, that's 0.06 watts, operating on 108.03 megacycles, just at the top end of the FM band. However, FM receivers cannot receive this signal, even though it can tune to the frequency, because the signal is amplitude modulated, whereas FM transmitters are frequency modulated. After 2 or 3 weeks, this 60 milliwatt transmitter will go dead because the batteries will wear out. But there is another transmitter operating at 10 milliwatts, sending out a signal on 108 megacycles, which can be heard as follows. Now, it's pretty weak, of course, but it will continue to send information back to Earth when the 60 milliwatt transmitter has died out. The batteries for the weaker one should last 2 or 3 months. The next chapter in American satellite history might be titled Explorer 2 Goes Awry. This will be explained in the following copy of a broadcast made to report this episode. The first signals that you will hear will be those from the transmitter in the Jupiter C rocket as it takes off from Cape Canaveral, Florida on March 5th, 1:30 p.m., 1958, and comes into radio view at Haverford College. As the rocket got up to about 150 to 200 miles, the second stage rocket went off, accelerating the satellite. Listen, you can hear the pitch change. Then here comes another push when the third stage went off. Now the rocket is up to speed. In a minute or so, the satellite disappeared over the horizon. In a couple of hours, we will know whether it was a success. As it turned out, it was not a success because the fourth stage rocket did not go off. Had we known at the time that there was a fourth stage, we might have been able to predict that it was not a success. In December 1957, the Navy attempted to launch its first Vanguard satellite, but without success. In January, unfortunately, they had another failure. But on March 17th, at 7:17 in the morning, the Navy made their third and successful attempt to launch the Vanguard satellite. This was also launched from Cape Canaveral, Florida. During the preceding 10 days, we spent many hours before the receiving equipment, scanning back and forth in anticipation of the launching. But every time, for one reason or another, it was postponed. Several mornings we had been on hand early because we had been told that the launching would take place. But unfortunately, we were not alerted on the morning that it was launched, so we missed it. However, at 20 minutes to 10 on the morning of March 17th, we picked up the signal from the Navy's Vanguard No. 1 as it made its first passage. Note that it has a characteristic wavering sound to it. That is evidently amplitude modulation to convey some information. As a matter of fact, it was a rotating system that did it, the spinning of the satellite. Now this satellite has a transmitter at 10 milliwatts. That is the signal that we're hearing, operating on a frequency of 108.002 megacycles, slightly higher than Explorer 1. There is also a solar battery located in this satellite, the satellite being about 6.5 inches in diameter and weighing 3.2 pounds. It has a solar battery in it, which will operate another transmitter at 108.03 megacycles at 5 milliwatts. But this is not audible yet, since it has to go around several orbits and have sunlight shine on the battery for a spell in order to get the battery energized properly. We will look for that signal later, but let us have one more listen to this frequency. That is not Doppler shift. That was me tuning the receiver in order to get it tuned in better. Now on March 19th at 8:45 a.m., we heard the solar battery-operated transmitter for the first time. It has a very vastly different modulation characteristic than the other transmitter. Here it is. The signal is not very loud. This is on 108.03 megacycles, 5 milliwatts. Now it so happened that Explorer 1 was going by just that moment, so we picked it up too. You can even hear the modulation in the background. Now that was a copy of a recording that was made at the time. The solar battery mentioned in that transmission is a small battery which derives its energy from the sun, so that as long as the sun is shining on it, it gives voltage and energy to a little oscillator built into the satellite. Since the satellite is expected to stay up 10 years or so, this transmitter should continue to operate satisfactorily for the life of the satellite. The frequency-sensitive element, which controls the transmitter on 108.03 megacycles, is mounted on the skin inside of the satellite so that it is at the same temperature as the shell. Since the frequency is determined by the temperature of the sensitive element, the temperature of the skin can be determined from the ground by measuring the frequency very accurately. This measurement is complicated by the fact that the Doppler shift has to be taken into consideration. The frequency shifts about 100 cycles per degree centigrade. The orbit of this satellite carried it to a distance of 2,500 miles from the Earth's surface. On about April 15th, it passed over us at this elevation, and we picked up its solar battery-operated transmitter. Or with a slightly different frequency tuning of the receiver, it sounded like this. Thus, these are the radio signals from man's furthest probe into space. Another dramatic moment in artificial satellite history was reported in a radio broadcast as follows. At 12:41 noon, March 26th, at Haverford College, we tuned in the Jupiter C rocket as it took off from Cape Canaveral in Florida. This is what we heard as we tuned the receiver. Now the receiver is set. The signal is not nearly so strong as it was in the first case. Perhaps it is the bad weather we are having here. This is a nice steady tone, whereas the Vanguard had a wobbling tone. This helps us tell them apart with all three of them up there. We heard only 3 rocket stages from here. Here is the last one. Note the frequency increase, which means the speed is going up. Now note this. Now the rocket has expired, and this pitch is about up to normal. It's about as fast as the rocket is going to go. Now we did not hear the 4th stage. At 2:45 or thereabouts, we should know whether it was a success or not. At 2:45 p.m., we heard a very faint and short duration signal indicating that the orbit was not as planned. Because if things had gone as scheduled, the signal should be very strong and should last for several minutes. Our deduction was that the satellite was very low. Thus, it came up over the horizon for only a short time. This would account for the short duration of the signal and its weakness. From the speed up of the rocket during takeoff, as indicated by the increase in pitch, it could be deduced that the speed was normal. This would mean that at the other extreme of the orbit, on the other side of the Earth, the distance would be large. It turned out to be about 1,730 miles. The distance at the near approach turned out to be about 120 miles. Let us listen to a few seconds of that short duration weak signal that led us to these conclusions. This satellite is known as Explorer 3. It has telemetering equipment in it and a small tape recorder. This tape recorder can record for 2 hours and then be triggered from a signal from the ground to send its signals back again in rapid succession. so that information can be reported that was recorded on the other side of the Earth. There has to be a small radio receiver in the satellite to pick up a signal from the Earth to tell the tape recorder what to do. This is the sound of the telemetering signals as they come down. With proper equipment here on Earth, these signals can be translated, as in the case of Explorer 1. Or again on another morning, it sounded like this. Thus, America has been able to launch 3 satellites in the short period of 2 months. The information that they will transmit to us about outer space will be invaluable in man's quest for knowledge. The following are excerpts from a recording made at Haverford College at the time of the Navy's second unsuccessful attempt to launch the full-scale Vanguard satellite. On previous attempts, we had noticed that there were odd signals on either side of the main steady tone of the satellite signal. We investigated these signals, as will be heard in the recording. Modulation from Explorer 1. Explorer 3. From Explorer 4.